Ladies and gentlemen, hello and welcome once again to the Database Revolution webcast series. My name is Eric Cavanaugh. I will be your moderator for what I'm sure will be a lively event. Obviously, we're focused on database. We're going to talk about the NoSQL movement and this whole topic of big data and big data analytics. Obviously, there are a lot of interesting things happening out there in the world of database. I'm sure you all have heard about that. So here's a slide about yours truly and enough about me. We have 4 presenters today, and of course this is part of our web report series. So what we do is we conduct research in a transparent fashion. So we want all of you to be able to see what we're doing and participate, to give us course correction, to give us ideas, to help us make sure that we are hitting all the proper issues and talking about things in a way that makes sense to all of you out there. So by all means, feel free to send in questions, comments. You can either do so using the chat or the Q&A, or you can also tweet with a hashtag of DBRev. This is the 3rd webcast in our series, and you can find out all kinds of information about this report at databaserevolution.com. There are several articles we've already written about different sponsoring vendors, and there are some other materials up there you can find to explore further what is going on with this database revolution. So we have 4 presenters today: Marc Madsen, Robin Bloor, Colin White, and Steve Dine, not necessarily in that order. Of course, Marc and Robin are the main analysts on this report, but we'd like to bring in other consultants and analysts to help us get a good perspective on what's going on out there. So both Colin and Steve are very busy these days. They're actively engaged with clients out there in the real world, so it's wonderful to have their perspective in what's going on. And of course, Marc and Robin do the same thing. But we'd like to get as many voices as we can reasonably fit in. So you can check out the recent events, the exploratory webcast, as well as the first roundtable, which had a couple other analysts on it, in particular Rajiv Rawat and Malcolm Chisholm. And Malcolm has already published an article at databaserevolution.com about his experiences. So now I'm going to go ahead and introduce Colin White. He's the president of Database Associates and founder of BI Research. He's been doing this stuff for a pretty long time. We're very happy to have him on board, as he always offers some insightful commentary. So now I'm going to pass the keys to you, Colin, and you should be able to just click on that slot and move on through your slides.
Thank you very much. Technology at work, right? And it's interesting that if you notice in my bio, I've added Database Associates back in the game, which was a company that I had many years ago when I specialized in database, and I'm back full circle now, working on database again. And as we were discussing before the webinar, Marc Madsen said I'm the setup guy, so I'm trying to set the scene, and the other guys are going to go into more detail than me, most probably. I think the title of my presentation summarizes things that I think the NoSQL movement's got a lot of attention as a result of big data, but big data to me is more than just about NoSQL. And so to start off, everyone defines big data. I personally think that the buzzwords become overhyped, but I think it is a useful term because I think a lot of these new technologies, including NoSQL, enable us to do things we couldn't do before. I think we need to look at this from a workload viewpoint, and I think we're now able to support workloads we couldn't support before either because of cost reasons or technology reasons. And I think there are 3 key technologies involved in big data. There's our traditional relational database products that have been optimized for analytical processing. There's the NoSQL systems that are the subject of this debate. I personally have an intense dislike of the word NoSQL. These are non-relational systems, and in fact some of them do SQL emulations, so to call them NoSQL I think is a bit of a misnomer. And then as we head more toward real-time analyzing data in motion, we're talking about stream processing systems. So these are the 3 key technologies we're going to use for big data. They actually should coexist. They each have their own uses, and the challenge, of course, is to understand where each one fits. And the key thing is, though, that they don't replace each other, they coexist. And so I'm sure you've seen many articles around the business case. I think, the big thing about big data, of course, is we get new sources of data. So that enables us to really improve our decision-making process. I think it enables us to do things better than we could do before. I think some of the new technology coming out enables us to do things much faster from an analytical viewpoint. We're now seeing people analyzing detailed data stores rather than having to aggregate data first before analyzing it. So I think we can do things much faster. Some of the predictive models I've been seeing, we see we can do things in a few minutes now that took many hours before. And that's a big game changer from a business viewpoint. And I think the other thing is that we don't always have to put this data in a data warehouse. In fact, a lot of the data we're analyzing in big data doesn't belong in a data warehouse. So that gets rid of IT out of the bottleneck. We can actually analyze this data outside the warehouse and get faster time to value. It doesn't replace the enterprise data warehouse. It extends it. So let's talk about non-relational, which is really the subject today. As I said, I don't like the word NoSQL. I think it's misleading. What we're talking about are non-relational systems. And we've had non-relational systems for years. I've been in IT far too long. I've actually been in it 40 years, and 40 years ago, I was working on a non-relational system called IMS. And so we had non-relational systems in those days, and they were optimizing for different workloads, and it's the same with non-relational systems today. We can use them for different kinds of workloads in the same way as we can relational products. I think the big difference about non-relational systems today is they do exploit parallel computing. Many of them are in open source. But the other thing is, they may be a group of products, but many of them do different things. There are a whole load of different types of data stores that are designed for different purposes. But of course, the industry very much is focused around Hadoop, which is the distributed computing platform. In a way, comparing Hadoop and MapReduce to relational is an apple and oranges comparison, because a lot of the time we're comparing a file system with a database system, which are quite different. But of course, things are changing. We now add Hive to Hadoop to give an SQL emulation there. We're adding some of the MapReduce functions to relational databases. So the comparison is getting a little complicated. And of course, we have a lot of people saying, well, Hadoop with Hive replaces RDBMSs. That's not true. They're designed for different purposes and different workloads. But as it says at the bottom of this slide here, I see organizations using a mixture of these different systems. In the same way as we used network and hierarchical systems in the past, we're going to be using these non-relational systems for certain kinds of workload. And we will continue to use relational products, particularly those optimized for analytical processing. And the challenge, of course, is when to use what. And I think Marc and Robin have been doing research in that area. And then the other challenge is to interconnect the systems. We are going to be moving data between different systems. The concept by which we have one enterprise data warehouse that contains everything, that's gone. Enterprise data warehouses will form the core of our analytical systems, but we're going to surround them by these other solutions that are optimized for particular workloads, and we need to make these systems work together. I think one big use of big data is investigative computing. At the bottom of this slide, we see our traditional environment by which we extract data out of structured systems into enterprise data warehouses and analyze that data. But I think for certain kinds of data, certain kinds of workload, more and more we're going to be using people like data scientists and data miners and things, investigating ways of improving our business, looking for new business opportunities. And a lot of that data will be multi-structured in nature, and you can see the kinds of data on the left. We will bring data from the enterprise data warehouse, particularly multidimensional data, to enable us to actually analyze that information. And then we'll actually run these analytics on investigative data platforms that may produce analytics. They may identify data we want to put in the data warehouse downstream. So this kind of picture is the kind of construction we're going to make. Those investigative computing platforms may be analytical relational products. They may be certain kinds of non-relational systems. The key thing is they coexist with what we have today. And so I have I think I've used up my 7 minutes, but one very interesting report I came across recently was the McKinsey report, which they did a superb job. I put the reference in here. It talks about all aspects of big data and what they were trying to look at, really the different kinds of applications. It can be applied to the business benefits. That one aspect of this that's also interesting is the little statistic at the bottom that says it's going to create 1.5 million jobs in the U.S. We keep talking about data scientists. I think these people are more than back office data miners. They're front office people who want to leverage big data for business benefit. They are going to be using a lot of the technology we've used in the past for things like data mining. But we've got to make this stuff easier if we're going to achieve that $1.5 million number. And quite frankly, some of the new technologies that are coming out, as Steve Dine will tell you, are still immature. And we don't want to have to train hundreds of Java programmers to do this. So I think not only is it a question of choosing the right database product for the workload, I think you also got to match it to the skills of the person. We simply can't train $1.5 million people on all this low-level stuff. We need easy-to-use tools if we're going to use it. So that's my 2 cents worth, and I'll hand on to the next speaker.
Okay, excellent. And Robin, I'll go ahead and push your slides for you. So that is our very own Robin Bloor, Chief Analyst at the Bloor Group. And your first slide is now up, the hardware landscape.
Yeah, I mean, what I thought I'd do here was what I suspected that none of the other guys would do, which was just try and paint the landscape that's led us to what we've been talking about as the database revolution. We are witnessing products that have been well established and that have been mainstream for 20 years getting superseded in various workloads by wholly new products. And that's, you know, something that it's worth understanding how that comes to pass. And I think the answer to that is really a product that was architected, you know, 20 years ago, was architected for a completely different hardware environment than the one that exists now. So I just thought I would run through what's actually happened to the hardware environment. When I started working with database, I think it was a little after Colin started. I was working on digital VAX with a product called RDB, which is not used much anymore. And in those days, you had one processor, a bunch of memory, a number of I/O channels and disks, and it was just a one-server thing. And then we moved to this kind of clustered arrangement where you had multiple servers all tightly networked together, and a database would go on there. And the environments we've got now are just completely different. I mean, first of all, in 2004, after decades of CPUs getting faster and faster, primarily by miniaturization and increasing the clock speed, it became impossible to improve the speed of a CPU by increasing the clock speed anymore, simply because there's too much voltage loss on the surface of the silicon, and it all turns into heat, and it doesn't do any more work the more you ramp it up. So the CPU designers went multi-core, which meant they put multiple processors on a single CPU. And since 2004, it's kind of been doubling every 18 months or so. We're kind of now up to 16 CPUs, I think, or in that kind of area, on a single core. Well, with 16 CPUs, you can spread the work out in a much different way than if you have one CPU. I mean, you know, you can have 16 different jobs running, each of which is multi-threaded. And you just couldn't have that in the old days. So first of all, the whole of the threading and the processing architecture of the database can change. Secondly, we've had this memory and disk cost ratio has fallen apart. The figures actually suggest that within about 5 years, memory and disk will be about the same price. That's solid-state memory rather than RAM. But the implication of that is, of course, that an awful lot of databases were fundamentally trying to make up for the fact that disk is slow, so they'd be caching as much as possible in memory, and they'd try and have the fastest possible caching algorithms and so on and so forth. Well, those databases that we were trying to speed up in the 1990s, you can pin the whole database in memory now. And they're just not a problem, you know, in the sense that the performance, you're going to have to find some really odd workload for those kinds of databases to actually cause any kind of performance problems with them now. And you know, one thing that happened through the 90s, at the beginning of the 90s, everybody was saying, well, can relational databases ever go fast enough to do transaction processing by the end of the 90s? Nobody asked that question. Nobody even thought to ask that question because hardware had just killed the problem. I mean, the databases had been improved as well, release by release, but most of that was just gifted by hardware. We then got this problem with speed of random reads lagging the speed of serial reads. Nowadays, and this has got to do with column store databases. Column store databases are just reading serially off the disk. They aren't doing random reads, or they're avoiding doing random reads. And the reason for that is that when you read randomly off a disk, the head moves. And the head move is the slowest activity that the disk can do. So the best thing to do is just spin the damn disk and just slowly move the head across it and pull all the data off. And that makes a difference to the way that a database works. Then we got extraordinarily fast networking now with fiber channel and fiber channel getting faster and faster. And faster switches. So the idea of clustering together a large number of machines like 10 years ago, that wasn't something that was easily achieved. Now you can cluster together a vast array of machines, and you've got extremely fast information passing between each individual machine. And this gives you a capability of scale out you would never have previously had. Parallelism, it used to amuse me that parallelism was never implemented in anything in IT except in databases. Databases pretty much had to be parallel because they had this concurrency problem. It would be okay to, you know, do transaction by transaction by transaction if it didn't create a lag. So you couldn't have, especially with mixed workloads, where one transaction might, you know, sweep across a vast amount of data, and the next transaction might just want to pick one piece. So you actually had to have parallelism in databases, and that was built into the relational databases. But we couldn't do parallelism in those days in the way that we can do it now, because we just have this much broader array of things that we can make happen in parallel. Then we got commodity servers, which means that in one way or another, the software has to be architected to run on commodity servers, because then you don't pay the price for the big Unix box. And then we got cloud computing, and that's going to cut, or well, already is cutting hardware costs again, but we've now got cloud computing where you can actually have grids of computers configured for you. So the hardware landscape just changed completely. And I would say that that's one of the things that provoked wholly new products appearing. Okay, next slide.
All right, I like this slide. Go ahead.
Right. This is the MapReduce thing. And I kind of get irritated with this. I'm like Colin, I agree NoSQL is a bad word. I also think MapReduce is a confusing thing. MapReduce is a processing capability. It's not a database capability. It's an algorithm for parallel processing. That's all it is. You can put MapReduce over a specific set of problems within the MapReduce software. You can program Java stuff, and you can make a lot of stuff happen in parallel, and you could do it with big let's say statistically intensive jobs on relatively small amounts of data. MapReduce isn't anything, in my opinion, to do with database. However, it was something that was brought forward with Hadoop because there was no free, easy way to make stuff parallel. So now, in my opinion, what we've got is we've got this strong association between what is a processing algorithm, and therefore you could use it in a database, but it doesn't have to be used in a database. It wasn't specifically designed to be in a database. It's specifically designed to actually work well with data partitioning. This is the top picture on the slide here, where you just break up the job into all the different pieces of, in this instance, 4 streams of data, and you run the processing against the 4 streams. You get the answers out the back. Well, it's worth noting that there is another kind of partitioning which can be equally effective depending on what you're trying to do, which is you break the processing up and you just cycle the data around 4 pieces of processing. And neither of these are more efficient than the other, and certain circumstances, one is better than the other. And the best situation would be to actually have both of these possibilities in terms of how you actually parallelize processing. But with MapReduce, you kind of stuck to data partitioning. So I would say, you know, it's not necessarily the be-all and end-all of parallel processing anyway. But, you know, not to take from it, you know, what it does very well. And I wanted to add, there seems to be this impression, and I think now that Hive's been put over Hadoop, I think the impression is just going to grow and grow that Hadoop is some kind of database. I don't really see it as a database. I mean, first of all, it is fundamentally a file system, although databases are. It's just that databases manage their files, where Hadoop does very little to actually manage its files, except it replicates them for in case of failure. And Hadoop, for most of the use cases that I've come across, it's just been used for ETL. In other words, you've got this huge big heap of data, maybe that's arriving at you know, at the rate of a terabyte a day or something, and you're sticking over the top of it some kind of process, but all that process is doing is sifting out the data you now want to look at. So at this point in time, that's what I would say is the major function of Hadoop. Next slide, Eric.
Okay, go ahead.
Right. This is really, I'm setting up Marc Madsen because Marc's got a much better perspective on this than I am because he's been working in this area. But the point is that the devil's in the workload. And if you look at this diagram on the right, on the left side, we've got more structured data. We've got RDMS giving way in terms of speed for going at large volumes of data to column stores. And that possibly will give way to big table. And that's all about structured data. And the thing about big table is that it's just one big table. Because it's just one big table, you don't necessarily have a join. Because you don't have a join, you can have a database that can call itself NoSQL, right? Because it doesn't have full support for SQL. But if it can't do select and project, then it can't do anything, really. So it will be doing those things, but it won't be doing joins because there's nothing to join. You know, so that's one side, and then what I would call less structured data, which Colin referred to. Well, those are really I kind of think of them as object databases. They had awkward structures within any given entity, if you like, and because of that, they didn't fit well into relational databases. So although object databases didn't gain huge traction in the market, they certainly carved out niche areas where they were used rather than the alternative. And, you know, with the advent of the web, that turned into document stores, and it's kind of, in my view, or the way I think about it, it's more like an XML store now, where you can, XML allow you to specify just about any kind of data structure. And that's on the other side. But if you look at this, you know, big data can be big unstructured data, or it can be big structured data. And if it's big unstructured data, then maybe you want to be looking at these NoSQL, so-called NoSQL things. And if it's big structured data, you still want to be in the relational database line because you still want all of that set processing. You know, unstructured workloads rarely suited traditional RDMS type engines. But, and here's where I think people are going to start making mistakes, is analytical workloads can be on either side of this line, you know. And analytical workloads are normally pretty hard to actually get right. So next slide, Eric. This is my parting comment.
Yep.
If you don't know the expected workloads, you shouldn't be selecting a database.
Oh, that's pretty funny. Okay, good. Well, let's move right along here. Analyst Steve Dine is next. And Steve, do you want to push your slides? You want me to push them? What do you want to do?
I guess I should push them.
Okay, I'm making you the presenter right now. Just click anywhere on that slide and hit the down arrow to go forward.
Okay.
There you go.
Thank you, everybody. Today, I wanted to talk a little bit about, actually a lot of bit about NoSQL and, as Colin would say, non-relational really from the trenches. It's something we've been working with now for the last few months with one of our customers, and sort of brought an interesting perspective. And obviously Marc Madsen and I teach on part of our course on non-relational and enabling BI for the 21st century, and so I'll share some of my my reactions from that as well. So why non-relational? I'll use non-relational instead of NoSQL in respect for Colin. But obviously more of everything, and more data and more different types of data, and we're having to manage more frequent changes to the data and the structure of the data. We have we have a lot of warehouses and data BI programs out there that are providing value but are maturing, and businesses are looking for more value out of the data, and they're looking for not just analysis on a sample of the data, but the entire data set, looking for outliers and looking for things like sentiment analysis and fraud analysis. And so the types of analysis are changing as we're looking to get more value from our larger data sets. And obviously there's a desire for more affordable and more affordable solutions that companies can take advantage of, especially as hardware prices come down and price of disk comes down, and our ability to distribute data over larger numbers of servers. And the last point I'll make on why NoSQL is there is a lot of buzz around NoSQL, and a lot of companies are talking about it. The industry is talking about it. Vendors are pushing it. There's a lot of venture capital money in it, and it has a large community, which are the programmers out in the world, excited about it, as it's a platform for being able to not just write large amounts of data and return it very quickly, but also the ability to work outside the realm of a structured database. So why not NoSQL? This is sort of an interesting play on words, because as I was playing with this, I was thinking, why not NoSQL? But that doesn't really get across my point, which is there are a number of areas we found working in the trenches with it that I think a lot of companies that are evaluating it need to consider. And one, obviously, that Eric mentioned is that it's very immature, and it is. And things like, and we've been working recently with MongoDB, and it's always fun, to when a data store or a database, whatever you're working with, doesn't actually return an error message when you make a mistake. That obviously will trip up a number of people that are working with it, but in this case, it doesn't. It just returns 0 records, regardless of whether you got the query right or wrong. And another challenge with it that we found is that, obviously it's, the stability of the system isn't always there, and it does take a fair bit of work as you're working through a project to, to obviously learn the systems. But, as these products mature, we'll see more management of these systems and the ability to run them in much higher availability environments. And my second point is it is very difficult to describe to decision makers what NoSQL or non-relational is. And as you're making a decision about what technology to use and trying to have the decision makers on board with the direction you want to go, it's very difficult to explain why you might go in this direction and what these are versus traditional databases, which nowadays, the majority of people understand. The third point is that maybe it's not fit for the purpose. And right now, as I mentioned, there's a lot of buzz out in the marketplace, and a lot of people just want to try and test it, and in some cases want experience with that technology, but they don't think about whether it's really fit for what you need it for. And as Robin had mentioned, these tend to be more around sequential access to the data versus random access to the data. If you're looking for low latency and you have a heavy amount of updates are occurring in your database, especially your data warehouse, where you see a lot of updates to the data, and you need complex joins, these aren't the systems, or at least right now, aren't the systems for for that choice. And so you need to think about what's fit for that purpose that you're leveraging it for. And also, what we found with our clients as they've talked through and asked us questions about NoSQL and whether or not to use it is, they're trying to figure out what the solution is or what the problem is that this is going to solve. And they feel like they need to leverage it and they need to utilize it. But in their cases, it's really a solution looking for a problem, and not every organization has that problem. And so, you really need to think about what is the problem you're trying to solve. Third is, and I put lack of BI support, and what we're finding, in BI being business intelligence, is that, as I mentioned, there's sort of two communities out there, and what we're doing, with business intelligence is a little bit different from, what we might be doing, for large-scale websites and, hundreds of millions of writes per minute or per day, and it's, these systems were originally designed for, large-scale distributed processing for web type analytic or web type systems, web type applications, and from a BI perspective, obviously we're seeing, for instance, in Hadoop, the ability to leverage Hive on top of it, and then DataStax that's sort of built that MapReduce connector into Cassandra. We're seeing the ability to start utilizing it a little bit more for BI support. Obviously, HBase that sits on top of Hadoop, we can leverage a little bit better for BI. But as far as supporting the common tools out there, there's just not a lot of support out there, and so we're left to really the programming aspects of it. And the last point is we do have a really major skills gap, and that skills gap, the skills that we have today in most BI environments aren't necessarily the skills necessary for for building up and working with a large Hadoop cluster, or implementing Cassandra or MongoDB, and putting data into it and getting data out of it, and writing a MapReduce job. These aren't skills that we find generally in BI teams. These are skills we find in our programmer teams. And one of the areas that we find to be the biggest challenge is and obviously it's a relative world, and I hate to use absolutes, but the majority of people that we run across that have experience with these systems, come from the programming side, and they don't truly understand BI and what the use is for around BI and analytics for these types of systems. They're leveraging it for other types of purposes, and so just hiring in someone that has these skills but no BI understanding or BI skills isn't necessarily fixing the problem. And so, we have a gap between sort of the SQL world and the NoSQL world, or the non-relational, relational and non-relational world. And these are, a challenge. I mean, finding resources on our BI teams that understand JSON and, can write Java and MapReduce programs and understand distributed data stores and distributed computing, and also, being able to architect, in a different type of realm where, we're architecting for key value stores and column family modeling. There's not a lot of information out there necessarily on it, and there's not a ton of architects out there that have this type of experience. So we really need to start trying to bridge this skills gap if we're going to leverage these systems. So some conclusions that that we've drawn from our experience leveraging some non-relational solutions are, it is best to evaluate your, what are your data sizes and your data growth, your formats, your structure, what are your analytic requirements before you decide on a solution. As Robin mentioned, should you be choosing your solution before you really know what you need? And the answer to that is no. I mean, just leveraging a solution because you believe you have big data. And by the way, from my perspective, big data is a relative problem, and it's not absolute. And so, what you may think is a big data problem, company next door likely is probably would maybe not consider it a big data problem. But having said that, you really need to evaluate your true requirements and then choose your solution. And make sure to evaluate, obviously, your skill sets, because experienced resources just aren't that available, and that around these technologies. And if you're relying upon your BI, your internal BI team to implement one of these solutions, it is a long learning experience, especially if they don't have programming experience. And so you need to think about, what do you have in-house and what can you go out and find if you're going to go out and build one of these solutions or leverage one of these solutions. You also need to plan for additional technology risk in your project plan. As I mentioned, it's a learning curve, and these are immature products. And in one of our projects, the MongoDB has gone up and it's come. We brought it up and it's come down, and there's been some data loss. Fortunately, not while in production, but these are evolving products, and it adds significant technology risk in your project plan. So think about limiting some of that risk by starting out maybe with one area within your environment. You start out with staging the data using one of these environments, and then at least you have all your data available, and then you can push it into a more structured data store to start out with to reduce some of that technology risk, but you still have that historical data that you can run MapReduce or any type of analysis against that data. And just make sure to do your proof of concepts before you go live, because these rarely work in production like they work in test. And as you start putting load on them and you start getting more users that are more dependent upon the data that you put out there and reporting structures that are dependent upon the data, it's different. So make sure you do your proof of concepts. And then, it is a very maturing market, and from my perspective, it will likely continue to evolve into a hybrid solution. We're seeing that today, as products like Retrieval and others start building MapReduce into their systems. And I think you're going to start seeing, the distributed file systems that relational databases can leverage, along with block-based systems that they leverage today. And so, from my perspective, you're going to see that continue to evolve into a hybrid solution. And so, be careful to close your eyes, because tomorrow things might change, and you just have to really be able to adapt to that change if you're going to leverage one of these solutions.
Yeah, very, very good point. And folks, last but certainly not least, let me hand the keys of the WebEx over to Marc Madsen of Third Nature. You should be able to click anywhere in that slide and use the down arrow to move your slides forward.
Okay, I will
there you
give
go.
it a shot. So, I'm Marc Madsen. I'm just going to give a short sort of talk on continuing some of what Steve was saying around technologies and looking a little bit at workloads and fit for purpose. So there's a few things. Colin laid out the conceptual basis pretty well, and I liked his definition. So I'm just going to look a little bit at the big side. Now, when we talk about big in big data, usually people are talking about volume, but it's often not specified that the volume is more than just amount of data. It's also concurrency, number of users, and it's computation. So there's really three axes for a volume problem. And those three axes are really important because they drive different hardware requirements, different software requirements, and are going to characterize different workloads. So the thing that you see most often with Hadoop, for example, MapReduce, these are computational workloads for the most part. It's very seldom that they creep over into what we would consider database workloads in the traditional retrieval and query sense. The concurrency side is likewise an interesting thing. Relational databases are decent at concurrency, but at extreme high-end concurrency, they really start to run into challenges. And if you throw high amounts of any of these other two things into the mix, it gets pretty complicated. The focus on big data also tends to focus on the data side quite often, talking about, one of the things which I personally can't stand. There's actually so many things I can't stand about the market right now. Big data as a label being one. I think NoSQL is kind of a misnomer, given that everybody's coming up with a SQL-like language to go with their NoSQL database, because it turns out that while you can build an application with a single access path and it behaves really well, most of the time you need to use that information for something other than just the interactive components of that application, at which point you need to do things like join data or get it out of that system and into some other system for analysis, for query and retrieval, for whatever the problem might be. Now, one of the aspects of the whole 3V thing with volume, velocity, variety, is the variety usually tends to imply not the traditional 6 or 7 basic data types that you find in a relational database. And I think that's good because it's a start. But there are the basic, what we call atomic data types, and then there are data structures. And that's where people start to talk about unstructured data. And unstructured isn't unstructured, it's unmodeled. The challenge is hierarchies and nesting and network linked structures inside of both the data collection, or the table or database itself, and even within what would be the single unit of stuff that you're storing. In an object or a document database, a program is is punting a bunch of data in a single object, which might map to a schema, typically to map to a relational schema from that object or nested structure, you're going to have to flatten it out, normalize it, and do things which make it hard to deal with from a programmer's perspective. But it still has a schema. It's just not a relational schema in the traditional sense. And so the problem is that most of this stuff is unmodeled data. It's not that it is lacking in structure. And the challenge there is the complexity and the mismatch between what a program wants to do with a data structure and what people retrieving or analyzing data want to do with that self-same data. And so the holy grail of databases in today's market, and I would lump into database all sorts of things, NoSQL databases, MapReduce, Hadoop, is the complexity problem, and the holy grail being solving that, which is the marriage of computation over somewhat more flexible schema structures that encompass things like hierarchical and nested and object or networked structures within the data, within the individual data elements and across data elements or across tables of data. And the problem that you find is that this is actually a mismatch not just for relational databases, it's a mismatch for NoSQL databases as well. Neither one is really good at this stuff. And I think, going back to what Robin said earlier, an important aspect of the Hadoop MapReduce is that it is a programming framework. It is not a database of any sort. It's a storage system, basically files with minimal file management, and code, a parallel code execution framework. And so it sort of abstracts in a different way from either non-relational or relational databases. And so you really have a triumvirate of technologies here. Now, if we're getting down into a specific project, you're facing a project, you want to solve a problem, you first have to diagnose it. And you have to diagnose it by really stepping back and looking at what the project itself is trying to achieve and what the nature of the workloads for that project are. You're designing a system. The system's got a workload. You need to know that, just like you need to know the symptoms, the core symptoms of an illness before you can begin to properly treat it. So that really boils down to workload. A lot of times I see really simplistic statements for any project, whether it's a database project using Oracle or something like Steve was mentioning using Mongo or Cassandra or whatever it is. Throughput and response time aren't enough. And a lot of times developers building web apps, for example, which might even, they're beyond your simple transactional or read-mostly web apps, but might even include complex queries and summations and other things like an account portal for customer self-service that goes back and sums up all of your account totals. Well, yes, you can do that in a relational database pretty easily. Depending on how you structure it, you can do it in a NoSQL database. You can build it different ways, but your real challenges are usually specified as throughput and response time. And if it's 100 simple queries accessing this month's to-date account balance stuff, it's pretty easy. But if you start throwing in a few complex queries with 2 years of history, you have to start pre-staging data and doing things we used to do in the slow hardware era of relational databases, which means all sorts of processing to position data up front, which becomes very fragile in a system design context because those things change over time. If you take the heavy-duty analytic things like a hazard calculation, which is basically looking at when customers might defect for an entire customer master, that's taking every transaction over a period of time for every customer in the entire system and going through it one or more times sequentially, which is a huge sequential process, which is different from the previous two things. And when you look at what you've got, typically your performance problems they're usually not a single factor, they're multiple factors. One big query, many small queries. Two things to look at beyond this whole throughput and response time are the retrieval and the selectivity. Are you returning a small set of data, a few rows, a single object, or are you returning 100,000 rows or 100,000 objects which you have to iterate or do something to, or just deliver to an application to do something else to. And likewise, the selectivity, are you selecting from a large collection of data a small or a large amount? Basically, are you scanning every single row in this data set, or are you just selectively pulling a couple of things out? You know, brute forcing your data, well, something like MapReduce is really great for that. But I just want a few rows, that doesn't work so well. You know, Hive for a few rows of data under high concurrency is basically a very sad experience. Now, another aspect to this is workload parameters, and this, I think, is getting to be better known today, but, you know, read-intensive versus write-intensive workloads, and read-biased or read-biased. You know, a lot of web applications are read-mostly, with a little bit of writing here and there as you poke in some user-generated content, or as you set up a web form that creates a user registration record or something. Others are very write-intensive. In particular, when you get into the analytics world, write-intensive things like collecting up clickstream or any kind of interaction data, log-based data, it can be very write-intensive, which leads us into, is the data mutable or not? Can you go in and change it? Does it change frequently, you know, lots of updates like a lot of OLTP systems, or is it largely immutable? Log records streaming out of systems are generally not updated after they have been extracted. They are what they are, and there's nothing else to do with them other than analyze them and possibly enhance or derive further information from them. And that information might be mutable over time, but the core data is not. Then there's this whole business of immediate versus eventual consistency. You know, if you're dealing with withdrawals from a bank account via an ATM, you need immediate consistency. You need the ACID compliance of a relational database. If eventual consistency is okay, you know, the count of badges on some website for the number of times something has been retweeted or liked on Facebook, who cares if it's off by even 5%? Eventually that number converges, and so eventual consistency is fine. And the same goes for a lot of things driving web applications. Well, okay, so it's inconsistent for a very brief period, maybe it's 10 seconds, but it doesn't matter when you query a lot of those things out, and over time they quiesce, and so you have the ability to trade off things like consistency, maybe or maybe not durability, which is a very different problem. And then, of course, short versus long access latency. Now, if you need this response in 300 milliseconds max to paint a web page, that's one answer. If you can wait for 30 seconds for a result to come back, that's a different one. And relational databases tend to be built for short access latencies, but maybe not short enough for a web app, but certainly a lot better than waiting for a Hive query to come back. And finally, predictable versus unpredictable access patterns. A lot of NoSQL, really good. This is true of pre-relational, you know, the parallel the NoSQL databases of today, the IMSs and IDMSs and things like that, was predictability. If it's predictable access pattern, if you know it's going to be joined in advance so you can shove it all together, and if you know that it doesn't change very often, the access path is driven by code, it's not driven by people, so an application-oriented framework, then you have leeway that you don't have in unpredictable data access patterns, because unpredictability means joins, it means relating data, it means the problems of a relational model that was designed to solve, and that leads you down a very different path. You know, that takes you down, say, Hive in the non-relational world, or a relational database, a parallel database, as probably a better solution to your problems. So when you're looking at these workloads, you can kind of lump them into, you know, on the write bias side or the read bias side, transaction processing. You know, there's nuance in that too. Batch transaction processing, where stuff gets batched up in collections, versus true OLTP, taking orders, processing orders, debiting inventory, looking at bank accounts and changing account balances, versus what I'd call OLTP light, which is what a lot of web apps do, where there's a read heavy, but still you have these writes going on. It's not read-only or read 99% of the time. And, you know, on the query side, business intelligence workloads can be simple, basic kinds of queries, or they can be highly complex many-table joins. And somewhere in between, there's this simple retrieval where I'm only pulling out of a single table. Well, that tends to favor, obviously, a NoSQL solution. And then, you know, you get into data types, hierarchical object or network structured data, where relational can fall over if you're not careful. So there's all these different models. And then, of course, the problem is that they're mixed. No system is 100% one thing. It's almost impossible to find those. And so when you find these mixed systems like inline analytic execution, which takes streaming stuff off a wire, executes something, and does something else with it while recording the data, like, for example, a recommendation engine or an operational BI workload, where the data is changing constantly underneath, where the data is streaming at high velocity, and it's being punted out in low latency. So how would you match these things up? Well, you can try to matrix this stuff out, you know, databases, parallel databases, NoSQL, which I'm lumping into that key value, distributed hash table, and object relational, and I would break out the whole Hadoop MapReduce mess as a very different ecosystem to either of these two things. And streaming databases, which Colin referenced earlier. And what they're good for, and you'll find that, you know, like a standard relational database, under an assumption of heavy data scales, it starts to have problems, and you have to really think about other nuances of the workload. Eventual consistency for anything which is built under traditional ACID compliance database models, well, you can just hang up the phone right there. But these different solutions, when you look at individual parameters or aspects of a workload, tend to kind of work out pretty well. The problem is when you start to mix them up. Then the intersection of these parameters creates a problem. And there's this other aspect which we haven't taken into account, which is the workload factors. You know, are the queries that you're issuing against your data store complex? Are they highly selective? Are they low latency? Do I need a result set or a result within 200 milliseconds? Do you have huge concurrency? You know, a website at 200,000 concurrent requests versus a data warehouse at 30 concurrent requests is a very different thing. And that's where you see the problems with standard relational databases, which are somewhat or can be somewhat solved by shared nothing relational databases. And, you know, at the assumption of, say, low complexity queries, highly selective low latency, well, you see obviously from this particular slide that NoSQL can shine. But if you have to go back in history, a streaming database will not shine. So you actually have to figure out your concurrency, latency, and response time, as well as the historical aspect of the data, then chart your parameters, because these simple 2x2 matrix charts like the two that I've just thrown up here don't necessarily answer the question. It's actually a decision tree with these charts at the end of it, and that's how you figure out how to design for one of these systems. And so we come to Steve Dine's final slide, which is my final slide. Always build a proof of concept, mapping the things that you think will work well to your workload, because you're going to discover certain factors of your workload you didn't anticipate, and they'll oftentimes throw out what you thought was going to be your first choice. And so with that, we'll roll back to Eric for Q&A.
Okay, folks, and we have a whole mountain of excellent questions. So panelists, if you would, if you haven't already, scroll through that Q&A component of your webcast console there down. Usually it's in the bottom right-hand corner. And to start us off, I'm going to throw one of my favorites, because this is something that's always in the back of my mind as I look and see all these great projects, all these open source projects, and typically, it's my understanding, they were all, or most of them, designed to address very specific use cases, very specific scenarios, and most of them were designed to circumvent some of the traditional constraints built into the relational database model. But the big question I have is, okay, what does this all mean really in the long term? And one of the attendees has a perfect question for that. And I guess, Robin, I'll throw it out to you, and then anyone else who wants to jump on, feel free. So one of the attendees writes, the traditional players, Oracle, Microsoft, Teradata, et cetera, are betting on data control to keep their market share. In other words, store your data on their systems, proprietary appliances, Azure, Aster, et cetera, instead of generic Linux farms. What do you think about that, Robin?
What do I think about the strategy of those vendors?
Yeah, or do you agree with this, and what do you think about that strategy?
Well, yeah, certainly all vendors that have a very big footprint in the market always pursue a strategy of trying to retain that footprint in whatever way they can, normally by locking you in one way or another, a clever way. But I don't think that strategy is going to work in this instance, because I think it will be blown away by the cloud. You know, one of the things that the cloud does is it unlocks the cost lock-in that people actually have. However, you know, I think one of the things that is not examined, and we need to examine in respect of the new generation, the new kids on the block, is their actual data management capabilities. I mean, at this point in time, most people are talking about what can they do in performance terms, and what kind of workloads are they suitable for. But there is another question, is can they really manage data? And I would say the jury's out on that, unless I think Steve's probably the best person to give me an opinion on that, because he's been working with some of these products.
Steve, you want to comment on that?
Well, I mean, with regard to the ownership of data piece, I mean, I think that, I mean, it's a valid concern. There's definitely a little bit of conspiracy theory in there, but it's valid. I guess, you know, on the analytic side, you know, especially on the, you know, in the analytic appliances, I guess the piece there that, you know, I would challenge a little bit is it's not, you know, it's not like some of the SaaS vendors where it's just impossible to get at your data. So I mean, you could always take your data. You know, they have very fast unloaders, and you can move your data off and into something else. You could even throw it out to a Hadoop cluster, or you could throw it out into, you know, Cassandra or wherever you wanted to. So as far as ownership of data, I'm not sure. I mean, I think what they're trying to do is, you know, provide a platform to, you know, to provide, you know, specific workload requirements and be able to address those and you know, solve specific needs. But as you're seeing, they all solve specific, you know, or address specific needs and requirements. So I guess I'm a little less about the ownership of data, because I think it is easy to move your data, you know, in and out. Obviously, there are some challenges sometimes with data types and things like that. But having said that, you know, I don't think it's insurmountable.
Okay, good. And Mark, maybe I'll throw this one over to you. It's a very interesting comment from one of the attendees. And folks, we'll try to get to all these questions, so we're going to go probably pretty long. We will archive this for later listening, just so you know. You can find that at databaserevolution.com. But Mark, one of the attendees, says, I'm looking for some silver bullets, any real-world success stories that can make NoSQL an easy decision. Granted, it's the way to go for a $70 billion company, but not a lot of those opportunities out there. And he says, let's face it, for $5,000, I could put together a system that uses SQLite, does 500,000 plus random IOPS, and has over 1 terabyte of solid-state drive data. Just a few years ago, it would have cost over $1 million in Iron and Oracle licenses to do that sort of work. What kind of workloads cannot be fixed in that fashion?
I think that's a really great question. You know, and the answer lies in the workload. You know, that 500,000 IOP per second system is really great, except that if that isn't a true shared nothing database that has the idea of a single schema over that, you will never be able to easily query that data in any appreciable fashion. So if the workload is build a website using something like this, you know, grab the open source Cassandra, Mongo, you know, choose your poison kind of database, you'll solve one particular axis, but you won't solve for all. And that's why I think we're in this fit-for-purpose world where suddenly the bottom drops out of your cost structure. You no longer need to buy $1 million in Oracle licenses plus $1 million in hardware to solve that problem. You can spend considerably less, solve that problem, and then your challenge becomes managing data across a distributed set of data stores that are built for different purposes. So unload that data from there, drop it into a shared nothing MPP database, which might be a Teradata or it might be something else. for your typical query purposes. And if you're trying to do computationally intense workloads, well, maybe you drop that into a Hadoop cluster and do something there, or pump it into a half-terabyte SAS data set for crunching. I think that's the world that we're living in now, because there is no one universal database. That's what Oracle and IBM SQL Server tried to become, and obviously they haven't quite succeeded for a number of different reasons.
Can I add my 2 cents with both questions, actually? I think the cost is coming down, and I think hardware, inevitably, costs are coming down, as Robin mentioned. I think also the advent of the new technologies is forcing the vendors to lower their prices. But it's back to Mark, well, I think we all said this, it's back to your workload. For individual point solutions and point workloads, you can build some things very inexpensively you simply couldn't build before. And we are going to use those solutions and cherry pick particular applications. But the heart of it is that directly you start to want to share data and have mixed workloads, and all the rules change. I mean, this is why some of these software companies love them or hate them. You know, they spent years developing good technology for multiprocessing, to handle multiple parallel applications, to do backup recovery and all the various utilities that go with it, to try and reduce the amount of workload involved, the amount of work involved in developing these systems. So it's coexistence again, and you know, you pay your money and takes your choice. And as Mark said, the challenge is you're going to find a solution that's much cheaper, but you've got to sort of manage this environment. That's going to be the key, I think.
Good point. And Robin, I'll throw this one out to you because I know you've been following relational for a long time. One of the attendees writes, can't relational technologies provide all the capabilities offered by non-relational technologies over time? If not, which areas do you see they would be challenged to do so?
Well, I mean, you know, Mark's kind of answered this in his presentation in a way. It's the unstructured stuff, especially the strongly nested data structures that relational was really never good at in the first instance. When you built solutions using relational databases for that kind of data, you were actually pretty much getting around the database for those, you know, particular objects that you were trying to process. You weren't actually using the database in a natural way. So, you know, if the question is along the lines of, can you push a relational database to actually do a lot of things where it isn't naturally good at? Well, yeah, you can always code it, you know. But you know, if you've actually built a particular architecture which is for handling documents, it's really going to do that job better. You know, all of the things being equal, and that's just the way it is. I mean, it's really horses for courses, and you can't get away from it. It's, you know, it's like if we put this horse on a motorbike, will it win the Kentucky Derby? The answer is no.
But the other thing, though, is an issue. It's something that Steve raised, is the concept of hybrid systems, where you have one system that has support to multiple languages, multiple data models, and multiple file structures. That way you can get the best of both worlds. In other words, rather than try and fit it to a particular language or particular structure, why we're around this management problem is this move towards some of the hybrid systems. And I think some of those hybrid systems are quite, have some potential.
Well, yeah, I think so too. Steve, go ahead.
I was going to say I agree, and one thing I would add is, you know, every database or data store has its strengths and weaknesses. They're all born out of solving, you know, certain problems and enabling certain capabilities, and so it is very, very difficult to say, you know, there's a silver bullet, and so I just, you know, you just have to really know. You know, what it is you're trying to do and whether that solution really solves it. I mean, we implemented a data warehouse in in MySQL, and you know, had a 450 million row fact table that, you know, try and throw an index, update an index on a MySQL table with huge volumes, and you know, it gets to be a challenge when, you know, you need to be up 24/7. So. You just have to understand what your requirements are. Everything from data sizes to response time to latency to, you know, availability. So you just have to really understand that.
Yeah, I think we came through a period when database technology was a commodity, and we're now entering a period, as Marc said, when one-size-fits-all doesn't work anymore because we've got new types of data and new challenges.
And folks, I'm going to go ahead and share my desktop here for a minute because we have a couple people asking for specific use cases for these types of technologies, in particular Cassandra and MongoDB and Hadoop, of course. And one of the sites I want to throw up here is a company called DataStax, and of course they are the ones who have built a solution on top of Cassandra. So if you take a look at this listing of companies, these people are all using Cassandra right now, and it's an absolutely amazing list. Now, a lot of these things have to do with, it seems to me, real-time concurrency, speed, and all these kinds of things. But, you know, so here's Netflix, for example. Netflix uses them. That's a case study that DataStax has. So there are just a whole mountain of companies using it. A lot of this stuff is Silicon Valley. I think that's kind of where some of this stuff came from. Of course, a lot of it is emanating out of Silicon Valley. But I guess maybe, let's see, Steve Dine, since you've been working some of these technologies, what are some other, like, what are some of the very specific use cases that you have encountered where people are trying to leverage this stuff?
One is you know, around weblog type data, things that change, you know, for instance, applications and things that change, you know, sometimes every single week, where the structure of the data is actually changing in the logs. And so it's much easier to accommodate those changes as you load it into, for instance, like a MongoDB or even Hadoop, where you're just bringing really the files in, or you're just bringing JSON documents in, and you're not having to go in, rework the entire schema, and then, you know, and affecting the entire table and running large update statements, that kind of thing. So it's you know, so that's one. Another is fraud analysis. I talked a little bit earlier about, you know, that long tail of analysis, and, you know, having to take the entire data set. So if you have extremely large data volumes that you have to iterate through, you know, using a non-relational system for that is very effective if you're looking for patterns and you're looking for things that, you know, across entire data sets, you know, things that lend themselves to programming, you know, in a much more iterative fashion than, you know, using, for instance, like a set-based language like SQL.
Okay, good. And let's jump to another question, Rob, and I'll throw this one out over to you. How do you see the future of some of these products evolving? For example, one of the people here mentions that Hadoop, I guess right now, has a limitation of 1 to 10 concurrent users, and obviously that's kind of an issue for some people, right? So what do you think is going to happen, just from your perspective, in terms of how these different vendors change their path? I'm guessing that they each are going to focus on their sweet spot and kind of build out from there. Is that a rational determination?
Yeah, well, and with the proviso that some of these vendors are only just, you know, are only just at market, so they've yet to properly establish what I would call a sweet spot. I mean, you know, the ones that we've mentioned, Cassandra and Mongo, they're actually fairly well established, and they've got quite a significant footprint, and they're obviously doing something very well. But when you actually look at Hadoop, I mean, let's, you know, just be realistic about what Hadoop is. Hadoop is an open source project, and you have had a whole bunch of vendors have done things with Hadoop. We got Astrodata, which, you know, created its own version of MapReduce and went off in its own direction. You've got Rainstorm that's put an in-memory database across the HDFS file system. You know, so once you've got something out in the open which everybody can play with Hadoop, you're going to get people doing things, not necessarily just from the open source perspective, you know, not just, you know, Hive's over there now, so we've got SQL over the top of it. Hadoop itself, the evolution of Hadoop is going to be a little bit like, I don't know, the first bird. I think there's going to be loads of different species of things that actually fall out of it. Plus, there seems to be almost a desperate desire on the part of every database vendor you run across to be able to explain what their Hadoop strategy is. So, you know, what we've actually got is a hotbed of innovation, and some of it's going to produce good results. And as usual, 90% will not be that good. But, you know, it's going to have good results. So it's actually difficult to say exactly where it's going to go, but I think it's going to continue to flower.
And Robin, I'll keep on you with this next one because one of the attendees asks, what about products like VectorWise? And I know you've written a blog about that, which will get much more advantages from a better usage of the CPU. In what cases would you go with something like VectorWise?
Well, VectorWise is fundamentally it's a column store database. So you would go in those instances where, from a proof of concept point of view, it beat everything else, then you would go with VectorWise. You know, outside of the typical column store type of data sets, I don't think the actual vector processing has any specific advantage. Because, you know, the advantage of the vector processing is that you're actually processing at the instruction level vectors rather than single instructions, effectively.
And let's see, I'll throw this next one over to, I guess, to Mark, and then anyone else feel free to comment on this. One of the attendees writes, as the amount of data grows in organizations, do you see a smarter way of analyzing vast amounts of attributes collected, such as statistical analysis and predictive modeling?
That's a very broad question, so it's kind of hard to answer. But yeah, I mean, the big thing with the complexity of data is that you have all these different data sets, and you have all these different files or tables full of information, and that's where, you know, the higher level picture, you know, moving out of just databases and looking at the whole environment, the architecture of data management and what it is that we need to manage and how. And that's where all the data management aspects that traditionally have been built up around a database become important. Database has a flaw in a single global fixed schema that's static in nature, but the tooling, you know, the various integration technologies that get and move data, the concepts of schema and metadata that allow us to find things in a database of, say, 1,000 tables, not that that's necessarily easy, and the tools that provide access to get and put data into and out of these things, as well as the tools that facilitate analysis. I think those are and always have been the weak spot. And as we get into this multi-store, multi-database environment, they become even more important than they were before. And I think, you know, what this really points out is that, yeah, we have the capability to crunch just about any data we want to in just about any way we want to, but the ease of doing that in a repetitive fashion as opposed to a series of one-off projects is still not there.
I'm going to throw one more question over to Colin because I think he may have to jump here in a moment. And I put this slide up that Mark put together, which I really think is exactly what people need, because you need to understand exactly what combination of issues you're dealing with. So what are the dimensions of your challenge in a particular use case? And you really need to think through then what is the best solution. And I think what the industry needs, frankly, is what we're doing in this report, which is trying to assemble some matrixed view of the different technologies and give people at least a head start in understanding which types of tools can be used to solve which problems. But Colin, do you want to just comment on Mark's slide here? That it strikes me as being a very useful tool to understand what you need to do, right?
Yeah, I mean, I think it's back to what Mark was saying. It is understanding your workload. You know, so across the top you've got various characteristics of workloads, and I think there are many other characteristics. But so it's workload, and then down the left-hand side, the technologies, like someone mentioned about Hadoop, you know, may not support the number of concurrent users some other systems have. And so I think it's a question of understanding the technology, understanding the various characteristics of the workload, and then matching them. In other words, I think there's a great tendency on these discussions to start bottom up, right? Do we need Cassandra? Do we need Hadoop? This, that, and what? But I think you've got to start off and saying, well, there are a lot of solutions we can build now we couldn't build before. given those solutions, what kinds of data do we need? What do we need to do with that data? What does that workload look like? And then look at the solution that best supports that workload. In other words, you start from the workload, not, do we have 9 petabytes of data? I don't really care how much data you got. It's what you want to do with it, how many users you got, how many different kinds of transactions are running in parallel, queries are running in parallel. So Marc's right. The concern that I have on the left-hand side is that, I think everyone's trying to be everybody else. In other words, I think a lot of the open source people are trying to reinvent the wheel. They're trying to solve problems we've already solved. I like to focus on areas that we haven't solved, so we can actually clearly identify workloads that we can support now that we couldn't before. But yeah, these kind of charts are useful. I think they're a starting point, but the bottom line, often, if you've got a really sort of workload that's pushing the extremes, the only way to find out is run a proof of concept. These kind of grids at least get you started, perhaps, of identifying a subset that would be useful running a proof of concept on.
Right. Okay, good. And Steve, if you have to jump as well, I understand. Folks, we'll go for probably another 10 minutes or so since we have so many of you still on the line, and we're really trying to dig into all these great questions. Thank you very much for sending all these questions in. And let's see, who have we not had lately? I guess maybe, Marc, I'll throw this one over to you. This is a question I get all the time when talking about these new database technologies. One of the attendees asks, is all this stuff complementary to a data warehouse, or can it replace a data warehouse? And one of the things that I keep thinking about is that the data warehouse in most organizations is a highly political project for obvious reasons. It's typically very expensive. And then if you're the guy in charge of the data warehouse, I'm pretty sure you're going to take the old if it ain't broke, don't fix it approach of dealing with things, any kind of a production system. If it's working, you kind of want to leave it alone, and you're going to be somewhat reluctant to make any significant changes to it. So I see this whole non-relational, NoSQL, whatever you want to call it, movement kind of growing up alongside of the data warehouse, and ideally organizations will take bits and pieces of what was in the warehouse or what they were relying on the warehouse for and start doing it outside of that environment to take pressure off of the warehouse. But what do you think about all that?
So, yeah, I don't see these things replacing a data warehouse. A data warehouse is designed for a particular workload. And one of the things that it was never really designed for, whether you take these old methodologies like Nimble or Inman, which are really just a, bottom-up database strategy versus a top-down usage model strategy for data modeling at their core, that's really what they were all about. And then you try to shoehorn something like machine learning algorithms on top of that. Well, that takes a different environment. It takes a different way of processing data, because the data that you use for those processes often cannot use the data in the data warehouse, because the data warehouse cleaned up the data. And the problem is that sometimes cleaned up, in the parlance of an ETL developer, means filled in missing values. And filling in missing values is a bad thing to do to machine learning data unless you know exactly how you're filling in those values, just as a simple example. And so you end up needing layered data structures or tiers of data support with raw data at one level for certain types of analysis and other information at other levels. So, simple query and retrieval for a fixed dashboard that's loaded once a day, you could easily prep that in Hadoop and slap it into a NoSQL database and build a dashboard over it. And it probably doesn't change that often, so it works great and gives you instantaneous response time. But that's not going to solve a BI query workload that a traditionally designed data warehouse is going to solve for more ad hoc, less predictable work. And so what you end up with is an environment where we probably have multiple things. And you can even see where we've gone in the traditional warehouse environments. A lot of people are doing analytic offload projects where they're taking data warehouse and they're taking statistical or other processing and they're dumping it into an application on top of a shared nothing, parallel database, an appliance like a Netezza or a database like a Vertica. and doing it in an adjacent model. And so we've got a collection, and I think, you know, it's kind of what Colin showed in his architecture slide. There are platforms to support the things we already understand, and then there's these platforms to support more exploratory, investigative, experimental problems, and then there are platforms to support application models. And I think we end up with technologies that line up under all three and maybe blur the distinctions a little bit as people figure out how to do some marriage of computation with traditional databases, and we end up with some new thing that isn't quite one or the other, but ends up being a little bit more of both.
Right, and Colin, I'll throw one more over to you before you have to jump. It seems to me one of the more exciting aspects of this new sort of database revolution that we're talking about is that it offers a different way of looking at some of the old problems out there. And let's face it, there are old constraints that were built into the relational database model which are now being circumvented by a number of these different tools. And while there are some risks along with that, for example, things like data governance and some other things, nonetheless, it does kind of open up the manner in which you can view problems. And one of our attendees writes, isn't the solution to dynamically project structure onto unstructured information and then dynamically configure queries for the specific workloads? He talks a lot about late binding, which I think is a really interesting concept, because now in traditional data warehousing, for example, there's all this work that has to be done to gather the data, to put it into the warehouse. You have to focus heavily on models and things of that nature, whereas now with some of these tools, because they have circumvented these old constraints, you can come to answers that again, are not going to be completely rivaling the whole world of a...
Participant lines unmuted.
Got some background noise going on back there. Real quickly, what do you think about this concept of late binding and of finding new ways of getting answers that don't necessarily have to go through the traditional route?
Oh, absolutely. I mean, that's the key here. In that, you know, we don't want to use. I mean, in some cases, people are paying a lot of money for their enterprise data warehouses, and no question they're looking for alternative solutions. But what's attractive about this technology to me is that we can actually build, you know, we can build new applications because we couldn't do it before, and we got new sources of data that we didn't have before. And if you look at that investigative computing platform there, in a way, it comes before the data warehouse. In other words, you know, traditionally we have a business problem, we identify the data, we put it in the data warehouse, and then we analyze that data. Often, you know, the users come back and say, no, that's not the data I want, or that's not the query I want, or that's not the model I want, or things have changed since then. With the investigative platform, you are trying to take, as Marc said, unmodeled data and trying to put some structure around it, trying to understand the business value and extract that business value. And in some cases, it may identify what data that you could extract and shove in a data warehouse downstream. In other words, you're before IT and the data warehouse designers, if you can call it sort of dynamic modeling, late binding, whatever you want to call it, but you're investigating this data to find out are there other aspects of business value you can get out of it, and either correct and directly generate analytics on it or models on it, or use it, as Robin was saying, as a transformation engine to extract the data out that you then put in the data house for regular analysis. So I absolutely agree with your point. That's the value to me.
Okay, good. And let's go ahead and wrap up here, folks. We've been going kind of a long time here. But, Marc, I'll give you a very specific question that I think is quite compelling. It's sort of a brain teaser. One of the attendees asks, if you parallelized the SQL command, could you use a streaming database to perform complex queries while maintaining sub-second latency with high concurrency? Or is it always a trade-off? One component must be sacrificed.
I think the answer is that something is going to be sacrificed. But, you know, the interesting thing with, say, a streaming SQL model is that, you know, if you have multiple streams representing multiple tables and you can converge those things, you can essentially do the equivalent of, you know, what you do with a complex SQL statement, which is the query planner breaks it up into multiple different accesses, joins data in different ways, aggregates data in different ways, and rolls it together. So it's a bit like stacking views in a federation tool, except that you're stacking hopefully time-aligned streaming queries and feeding them into each other. And I've never really tried to do anything complicated with a streaming SQL database, so it would be an interesting exercise.
There you go. Okay, folks, and let's see, maybe some final closing comments. Robin, Bloor, anything in this event that kind of sparked your interest, or anything that maybe you'd like to comment on further?
Well, I just thought, this is the best event that I've been a part of, I think, personally. I just thought it was an excellent discussion of workloads, and I think that apart from anything else, we got to the heart of the matter. This is what the research project is about, is it's discussing this stuff. And I just thought it went very, very well in that respect.
Okay, good. Colin White, any closing remarks from you?
Yeah, it was a good session, and we need more of this kind of discussion, because I think at the moment, there's a lot of confusion out there, and B, there's a lot going on in companies. In other words, if you move away from the traditional IT data warehousing group, you go and look at some of the people in some of the business units. They're doing a lot with this stuff, and it's important to understand what they're doing and how to leverage it. But I think at the moment we're in education role, because so many people are confused and there's so much misleading information out there.
Yeah, you can say that again. And not all of it is intentional. I will say I would
agree.
Yeah, I've been in the world of marketing, and if you're a marketer, what you need to do is get the attention of someone such that your top sales guy and sales engineer can go in and solve some problem and make a sale. So a lot of this confusion does just kind of originate from the desire to get somebody's attention so you can start talking about what you can do. Steve,
realize not everybody's at these extremes either, and that's the other thing.
That's right. That's exactly right. Well, as Steve Dine, as you mentioned, sometimes in a lot of cases it's a solution looking for a problem, right? Any closing comments from you?
I agree with both Robin and Colin. It's evolving, and I think the mass market is the mass market because the mass can use it and leverage it, and I think that starts bringing it down to ease of use and fit for purpose and those types of things. If you look at the changes coming down the pike, IBM is implementing their own stack, complete with an installer that will install basically every component of Hadoop, pre-configured onto your system. Not today where you're doing, you have to install each component separately and configure it. Windows, I think Hortonworks is developing Hadoop for Windows, and so you're starting to see it, evolve into more of the mainstream. Hive is another great example of where, it's putting a tool on top of something that more people understand and know how to have a better understanding that will help get data out of these systems. And so, I think I think one of the themes today was it's a fairly immature platform, and as it matures, I think we're going to start seeing more use cases for it, and I think we will start seeing more hybrid type solutions that you don't have to trade off as much, but maybe you can implement a solution that addresses a good part of what your needs are from a workload perspective.
Yeah, good. And Marc Madsen, I'll offer the final closing comments to you after I just mentioned one thing that I think is fantastic about this whole movement is that it really has put the pressure on the big vendors to kind of hone their skills and to improve the stuff that they had sitting around, because some of them certainly have done a fair amount to innovate their products over the last few years, but some of them kind of just sat back on their heels for a while. What do you think?
Yeah, that's exactly what I would say. For a long time, most of the traditional vendors didn't pay attention, and then about 7 or 8 years ago, we saw the advent, or not the advent, but the rise of the shared nothing databases, which quickly got taken out of the market by the big vendors in acquisitions, IBM with Netezza and so on and so forth. And so they kind of proved the market for that as a replacement on the query-intensive side. It didn't really affect any of the database vendors on the OLTP side. The thing that's going on in the market now, it's similarly caught them off guard, but you have to remember that these databases are, perhaps 20 years old at their core, and it's pretty hard to make a lot of changes to a software architecture that has been evolved and optimized for that long. And you've got cost structures built up around that. You've got whole organizations built up around selling a particular usage model at a particular price point. And I think that all of that inertia opens up the door to, to potential disruption. And I think that's what we're seeing right now.
Right, and to Steve Dine's point, don't blink because something could change any minute now. And the bottom line is we are at the beginning of what is a really, truly exciting revolution in the world of database. And I think we're going to see a lot more activity over the next 3 to 4 years as all these major players, not just the usual ones like Oracle and Microsoft and IBM and Teradata, but this whole new crop of vendors, many of which will probably fade away, but some of which will probably survive. And then you have these other companies like Google and Yahoo and Amazon and others all trying to solve very serious problems, and Facebook and Twitter and LinkedIn, all these concurrency problems, and lots of interesting innovations are just shaking out of all these projects. So keep your eyes and ears peeled, folks. And I put up 2 websites here with more information. The Database Revolution is databaserevolution.com. That is where you can find all kinds of information about this report. InsideAnalysis.com is our own website here at the Bloor Group, and I'll credit Marc Madsen with the idea of having a specific website where we marshal all this data. So that is databaserevolution.com. A survey is going to pop up as soon as you leave this event. Please do take a few minutes to fill that out. We'll greatly appreciate your input on that. And the final event is going to take place next month, so feel free to give us any insights you have via email, via Twitter. If you want to send us some postal mail just to be clever, do that. But we want to get your thoughts on what is happening in this world of database. So with that, folks, we are going to end the event, and we will archive this. You'll find a link to it at databaserevolution.com. Thanks again, all of you, for your time and attention. We really appreciate it. Take care, folks. Bye-bye.